Blessed day, everyone. Today we move on to our next topic, the approximate analysis of statically indeterminate structures. In this chapter, we will present some of the approximate methods used to analyze statically indeterminate trusses and frames. These methods were developed on the basis of structural behavior, and their accuracy in most cases compares favorably with more exact methods of analysis. The analysis when using a model must satisfy both the conditions of equilibrium and compatibility of displacements at joints. For an initial design, member sizes are not known, and statically indeterminate analysis cannot be done. A simpler model must be developed, that is, statically determinate analysis. The analysis of this model is known as the approximate analysis. The preliminary design of the members can be made, after which the more exact indeterminate analysis can be performed and the design refined. Vertical loads on building frames. Building frames often consist of girders that are rigidly connected to columns so that the entire structure is better able to resist the effects of lateral forces due to wind and earthquake. In practice, a structural engineer can use several techniques for performing an approximate analysis of a building bent. Each is based upon knowing how the structure will deform under a specific load. One technique would be to consider only the members within a localized region of the structure. This is possible if the deflections of the members within the region caused little disturbance to the members outside the structure. The approximate location of the points of inflection can be specified. These points are the zero moment points. The assumptions for the approximate analysis. The column supports at A and B will each exert three reactions on the girder. The girder will be statically indeterminate to the third degree. Since both ends of our girder connected to the column both are fixed, so it means each of these will have three reactions. Now, using the concept of the equations of equilibrium, which we have three, leaving us another three for unknowns. So we have three extra unknowns. That is why the girder will be statically indeterminate to the third degree. So we need three assumptions in order for us to perform an approximate analysis. If the columns are stiff, no rotation at A and B will occur. However, if the column connections at A and B are very flexible, then zero moments will occur at the supports. In reality, the columns will provide some flexibility at the supports. Therefore, point of zero moment occurs at the average point between the two extremes, which is 0.21L divided by 2, or that is approximately equal to 0.1 times L, where our L refers to the length or the span of our girder. So this is measured from our supports. In summary, each girder of length L may be modeled by a simply supported span of length 0.8 L resting on two cantilevered ends, each having a length of 0.1 L. The following three assumptions are incorporated in this model. There is zero moment in the girder, 0.1 L from the left support. Number 2, there is zero moment in the girder, 0.1 L from the right support. And number 3, the girder does not support an axial load. Let us take this one as an example. Determine approximately the moment at the joints E and C caused by the members EF and CD of the building bend. In this problem, we take note that the cantilevered spans supporting the center portion of the girder has a length of 0.1 L. Since the total length of our girders is equal to 20 feet, we multiply it by 0.1, which yields 2 feet. So the length of the cantilever span is 2 feet from each support. That is 2 feet from point E and 2 feet from point F. Also, we convert our distributed load of 800 pound per foot into a concentrated load after we were able to determine the simply supported span, which is 16 feet. So for our approximate analysis, we will be using this model, showing that our center portion is a simple support and our ends are cantilever spans. As you can see, our 800 pound per foot multiplied by 16 feet will give us a concentrated load of 12,800 pounds. For the reactions in the simple support spans, we will have 6,400 pounds. The cantilever spans are subjected to a reaction moment of 1,600 multiplied by 1, which is the location of the concentrated load from 800 pound per foot in the cantilever span, plus 6,400 pounds times 2, which is the reaction from our simply supported portion. This will give us a value of 14,400 pounds foot, or that is approximately 14.4 kips foot. Now, plotting our moment diagram, we will have this. At joint E and joint F, we have a value of negative 14.4 moment. Then, at 2 feet from the supports, we have 0 moment. And the midspan of our simply supported girder, or the simply supported portion, will give us 25.6 kip foot. So this is now the moment diagram of our whole girder. Portal frames and trusses. Portal frames are frequently used over the entrance of a bridge and as a main stiffening element in building design in order to transfer horizontal forces applied at the top of the frame to the foundation. On bridges, these frames resist the forces caused by wind, earthquake, and unbalanced traffic loading on the bridge deck. Portals can be pin-supported, fixed-supported, or supported by partial fixity. The approximate analysis of each case will now be discussed for a simple three-member portal. For our case 1, which is a pin-supported frame, or for a pin-supported column, we assume that the horizontal shear are equal. For fixed supported column, we assume horizontal reactions are equal and a point of inflection occurs on each column, midway between the base of column and the lowest point of truss member connection to column. For third case, the points of inflection on the columns lie somewhere between the case of having a pin-supported portal, where the inflection points are at the supports, or that is the base of the columns, and a fixed supported portal, where the inflection points are at the center of the columns. For portal trusses, in all cases, the suspended truss is assumed to be pin-connected at its points of attachment to the columns. Furthermore, the truss keeps the columns straight within the region of attachment when the portal is subjected to the side sway. Consequently, we can analyze trussed portals using the same assumptions as those used for simple portal frames. To understand this one, we will take this as an example. We determine by approximate methods the forces acting in the members of the Warren portal. The truss portion B, C, F, and G acts as a rigid unit. Since the supports are fixed, a point of inflection is assumed to exist at 3.5 meters, which is half of the 7 meters, above A and I, and equal horizontal reactions or shear act at the base of the columns. That is, the summation of our forces horizontal will equal to 0, giving us the value of our V equal to 40 kilonewton over 2, which is 20 kilonewton. With these assumptions, we can separate the structure at the hinges J and K and determine the reactions on the column as follows. First, using the lower half of the column, and then we use the upper portion of the column. For the lower half of column, we take moment at A. So we will have m minus 3.5 times 20 equal to 0, giving us the value of m equal to 70 kilonewton meter. Using the upper portion of the column, we take moment at point J, giving us negative 40 times 5.5 plus n times 8 equal to 0, of which our n refers to the vertical reaction at our columns. Now the value of our n becomes 27.5. Using the methods of sections, we can now proceed to obtain the forces in members CD, BD, and BH. So we will isolate the upper half of the column. Here, we will be using summation of forces vertical equal to 0, which will give us the vertical component of the truss member BD. And also, the other available vertical load or vertical reaction is the 27.5. So our equation for the summation of forces vertical equal to 0 is negative 27.5 plus FBD sine 45 degrees equal to 0, which will yield a value of our FBD equal to 38.9 kilonewton in tension. After solving for the value of our FBD, we will now move on to the computation of your member CD. In order for us to solve for the value of the force in our member CD, we will take moment at point B equal to 0, which will yield an equation, negative 20 times 3.5 minus 40 times 2 plus FCD times 2 equal to 0. Solving this one will give us the value of your FCD equal to 75 kilonewton, which is in compression. So here, we take note that our assumed direction of your FCD is compression. And the value of our computation gives us positive, which confirms the value of our FCD in compression. In order for us to solve for the member FBH, we will take moment at D, which will give us the equation FBH times 2 minus 20 times 5.5 plus FBD cosine 45 times 2. Now, we already have the value of your FBD, which is 38.9. So, we will substitute this one, and the value of your FBH becomes 27.5 kilonewton, which is in tension. You may now employ the concept of the analysis of truss using the methods of joint or section. So, compute and check if the values are correct. I will be giving you here the summary of the member forces. So, on your own, you try to check on if this is correct. Lateral loads on building frames using the portal method. A building bent deflects in the same way as a portal frame, and therefore, it would be appropriate to assume inflection points occur at the center of the columns and girders. If we consider each bend of the frame to be composed of a series of portals, then, as a further assumption, the interior columns would represent the effect of two portal columns, and would therefore carry twice the shear as the two exterior columns. The portal method for analyzing fixed supported building frames require the following assumptions. Number 1, a hinge is placed at the center of each girder, since this is assumed to be a point of zero moment. A hinge is placed at the center of each column, since this is assumed to be a point of zero moment. And lastly, at a given floor level, the shear at the interior column hinges is twice that at the exterior column hinges, since the frame is considered to be a superimposition of portals. These assumptions provide an adequate reduction of the frame to one that is statically determinate, yet stable under loading. Let us take this one as our example. Determine approximately the reactions at the base of the columns of the frame. Use the portal method of analysis. Applying the first two assumptions of the portal method, we place hinges at the centers of the girders and columns of the frames. A section for the column hinges at I, J, K, and L yields the free body diagram as shown. Here, the third assumption regarding the column shears applies. The exterior column will receive a value of V, while the interior columns will receive 2V. Now, using the upper portion of our frame, we sum up our forces in the horizontal direction. Our load is 1,200 pounds, directed to the right. Now, since our column shears, we have V, 2V, 2V, and V, which will equal to 6V. For the summation of forces horizontal equal to 0, we will have 1,200 equal to 6V, or the value of V is equal to 200 pounds. Using this result, we can now proceed to dismember the frame at the hinges and determine their reactions. As a general rule, always start this analysis at the corner or joint where the horizontal load is applied. Solving for the forces on segment IBM. Since the value of our shear at point I is equal to 200 pounds, if we sum up the forces horizontal equal to 0, we will have 1,200 pounds minus 200 pounds minus mx equal to 0, which will give us the value of your mx equal to 1,000 pounds, which is correct based on our figure here. Then, we sum up the moment at point I equal to 0, which will give us negative 1,200 times 6 from point B plus 1,000 times 6 at point M plus my times 8 at point M equal to 0, which will yield the value of our my equal to 150 pounds directed upward. Now, summing the forces vertical equal to 0, we will have my from point M and your iy from point I equal to 0, which will yield the value of iy equal to 150 pounds directed downward. Moving to the next segment, the value of our shear at point J is equal to 2V, or that is 400 pounds. Also, we will transfer the loads from point M from the previous segment, which is 1,000 pounds and 150 pounds. Summing up the forces horizontal equal to 0, we'll have 1,000 minus nx minus 400 equal to 0. Nx is equal to 1,000 minus 400, giving us 600 pounds as the value of your nx, which is correct based on our figure. Summing the moment at point J equal to 0 will give us negative 1,000 times 6 at point M plus 150 times 8 still at point M plus ny times 8 at point N plus 600 times 6 at point N, giving us the value of our ny equal to 150 pounds directed upward. If we sum up our forces vertical equal to 0, upward positive, we will notice that the value of your my and your ny is equal, leaving the value of your jy equal to 0. Moving on to our next segment, NOK. Again, the value of our shear at point K is 2V, which is 400 pounds. Also, we will transfer the loadings from point N. We have here 600 pounds and 150 pounds. Summing the forces horizontal equal to 0 will give us 600 minus 400 minus OX. Computing will give us the value of OX equal to 200 pounds, which is the same as to the figure. Taking the moment at point K equal to 0, counterclockwise positive, will give us negative 600 times 6 plus 200 times 6 plus 150 times 8 plus OY times 8 equal to 0, giving us the value of your OY equal to 150 pounds. Summing the forces vertical equal to 0 will give us negative ny plus OY minus ky equal to 0. Since our ny and our OY has the same value, then the value for ky is equal to 0. Moving to our last segment, which is OGL. For the summation of forces x is equal to 0, it shows the assumption for V is equal to the value of OX. Summation of forces vertical equal to 0 will give us negative OY plus LY equal to 0, giving us the value of your LY equal to 150 pounds. After solving the upper portions of our frame, we will isolate the lower columns with their respective loads from the upper half. So here we were able to transfer the 150 pounds and the 200 pounds at point I, the 400 pounds at point J, the 400 pounds at point K, and the 150 pounds and 200 pounds at point L. So here we will use the summation of forces X and summation of forces Y to solve for the reactions at X and Y of our columns. Then we take moment at the supports to solve for the moment reactions. Here, for point A, the value of your AX is equal to 200 pounds. The value of your moment at A is 1,200 pound-foot, or that is solved from the 200 times 6. For our point C, the horizontal reaction is 400 pounds, and the value of the moment in our support is 400 times 6, which is 2,400 pound-foot. For point E, the value of the horizontal support or reaction is 400 pound, and the value of your moment at point E is equal to 400 times 6, equal to 2,400 pound-foot. At point H, the value of your horizontal reaction is equal to 200 pounds, and the value of your moment at the support is equal to 200 times 6, giving us 1,200 pound-foot. Next example. Determine approximately the reactions at the base of the columns of the frame. We use the portal method of analysis. Here, first, hinges are placed at the centers of the girders and columns of the frame. Then a section through the hinges at O, P, Q, and J, K, L yields the free body diagram as shown. The column shears are then calculated. So we take note for our shear, the exterior columns will receive a value of V, while interior columns will receive twice the value of your shear, or that is 2V. So what you shall do here, you will isolate first the upper segments. So we will have the OGR, the RHSP, and the SIQ. Then, after solving for all the values of the loads, particularly the horizontal and the vertical loads, or the horizontal and the vertical reactions at the hinges, you will transfer that one to the lower part. Then, we isolate or we cut the frame at J, K, and L. So, the same process. We compute again for the value of your V, 2V, and V. Here I will show you the answers for our frame. So, on your own, try to compute if you will be able to solve for the same values.